Bismillahirrahmanirrahim. Starting second part of the ceramic and porcelain fused to metal chapter. Starting with sintered alumina core ceramics. As we have touched it in the previous lecture, use of alumina additions to strengthen porcelain has been taken a stage further with the introduction of the sintered alumina cores for one such system, that is in Ceramming. First stage in producing the restoration involves formation of a duplicate die using a special plaster. Duplicate die mean that we have made a die and we have to duplicate it and made an other die. An alumina slip already described in the previous lecture, prepared from alumina powder, and water is then painted onto the die. And the moisture from the slip is absorbed by the plaster. Which plaster? From which we have made the die, leaving a layer of alumina powder, which ideally should be 0.5 millimeter thick. And this then sintered by firing at 1120 degrees centigrade for 2 hours. When this firing done, the die material shrinks, not the core. The painted one not shrinks, only the die material shrinks. Keep it in mind. Due to which, when we have if we consider it is a die and it is the slip, and if the lower die material shrinks and core material remains intact, then its removal should be easy. So firing makes shrink die material and the removal of the sintered alumina core quite easily. Now, outer surface of the core then again painted with the slurry of a glass powder, and now it is fired at 1100 degrees centigrade, 20 degrees less than the previous temperature, for liquefying the glass, which flows and fill all the spaces between the sintered alumina particles. Now the glass used is lanthanum aluminosilicate. Why? Because lanthanum reduces viscosity and assists in filtration. It also increases the refractive index of the glass and improves the translucency of the ceramic. After microblasting to remove gross excess of the glass, refiring again, now again 40 degree more reduced temperature, about 40 degrees centigrade, 1120, 1100, and now it is 960 degree. Refiring is performed to ensure proper infiltration of the alumina with glass. So some variations are also there. On completion of the core firing, dentine and enamel layers built up in the traditional manner which I have previously described. Extremely high flexure stance indicates suitability of these for the production of multi-unit restoration, not a single unit restoration. And this requires use of cast metal substructure. Cast metal from cast, or the spinel based cores of magnesium aluminate have been used instead of alumina for this purpose. If we are not using metal-based substrate, then spinel-based cores of magnesium aluminate translucency was improved by, but these are not as strong as sintered alumina cores. Now, zirconium, further advances are developed and developments are there. Sintered alumina cores containing zirconium oxide. For what? To achieve further strengthening and a reported flexural strength of up to 800 megapascal is there. One limitation of this system is the relative opacity of the resulting core, because zirconium is opaque, and this is difficult to mask with glass infiltration and limit the aesthetic quality of the final restoration. Now comes injection molded and pressed ceramic. As obvious from the name, injection molded. We have discussed injection molding in the chapter of acrylics. And pressed mean obvious from the name, when we have to press it. These material was first reported in 1983 for the production of all ceramic single anterior or posterior crowns. All ceramic mean no metal. First commonly used commercial system based on this principle is Cerastore. And it involves the production of crown cores by injection molding. Injection molding, same that when we have anything and we have to inject it and fill the mold. So this is the injection molding, and eliminating the need for the use of platinum foil. Platinum foil wala kissa khatam. No use of platinum foil. And improving marginal adaptation of the crown. Close fit हो जाएगा ना injection molding की वजह से. So as we have a close fit and platinum foil, so our cost also reduced. Now spinel. Previously we have said that we are going to use spinel. What is this spinel? Non-shrink properties achieved by incorporating magnesium oxide into the ceramic frit. Then a mixed metal oxide is formed. Because magnesium is a metal, so this is called a spinel. Spinel is less dense than the original mixture of oxide. Its formation results in an expansion which compensates for firing shrinkage. It not shrinks, it expands. Now coping, you all knows about the coping. Anything which covers the other one and use as a cope, this is coping. Technique for fabrication ceramic copings coping mean in simple terms a cap. Yes. Technique for fabrication ceramic copings from this type of material involves the formation of wax pattern on an epoxy resin die. Already described epoxy resin die in previous chapters. And wax pattern, you all people know. A variation of lost wax technique. Lost wax technique also described in the previous chapters to maintain the correct shape and size in the ceramic material. Same as you people make the dentures. The mixed material containing magnesium and aluminium oxide, glass, kaolin, calcium stearate, and wax is injected under pressure at 180 degrees centigrade to the prepare mold. Then firing is carried out in the special furnace using controlled temperatures up to 1300 degrees centigrade, which promotes the formation of the spinel. Now, veneer porcelains are baked onto the surface of the coping to produce the finished crown. Veneer porcelains on the surface. Now you people well aware about the veneers. What are the veneers? So for giving shape or color or uh, aesthetic, veneering porcelain are also there. So veneer porcelain are baked on the surface of the coping. The cap, one coping main cap, which we have produced. Now the technique sensitivity issue is there. That these ceramic copings can be used for constructing all ceramic crowns for molars. Strength of the material is not much different from ordinary aluminous porcelain, but the complexity of the process and special equipment has limited its use. What is its main? Yes, this one, the spinel and injection molding and press restore material. Now IPS Empress. Further development of injection molding introduced by the name of IPS Empress. Molten feldspathic type glass is pressed. Now it is pressed into preform mold formed using a high temperature investment material and a wax pattern, same as previously described or as we described in acrylics, denture based material. After the molten glass has been forced into the mold under pressure, this is the injection molding. It allowed to cool under controlled condition. By doing so, reinforcing lucite crystals are encouraged to form. The properties of materials are similar to those of the cast glass ceramics. Now the cutback. What is the cutback? For characterization, one of the two methods we are using. Characterization means to giving the final shape. To characterize, to give the final touch. For anterior crowns, a layering technique is normally used to achieve the best possible appearance. Already described that we are using layering technique. 1 layer, 2 layer, 3 layer. So it is a layering technique. A fully sized crown is first produced from a wax pattern, as we have done in the denture base. But here, At there we have not made the crowns, but we have made the wax pattern. I am concerned about the wax pattern. So for crown, we are going to do same things. We are making the wax patterns. This structure is done then cut back. Cut back means we have to cut the areas. In those areas where conventional layer porcelain are used to give optimal aesthetic, to give adequate space for the veneering material. We have to cut back mean to make cuttings over there. And then we have to do the conventional layering. During the firing of the outer veneer layer of porcelain, further strengthening of the pressed ceramic core may occur as the contraction of lucite crystal increases. Already described that we have to wait for how long? For cooling of that material, and which allows reinforcing lucite crystals. So in this, concentration of lucite crystals also increases with the passage of time with the cooling. Then, and this Empress 1 was for the anterior teeth. For posterior crowns, IPS Empress 2 was introduced. Inlays or labial veneers even, either aesthetic or not, considered so important, or where layering would be impossible. Why layering is impossible? Because of the insufficient thickness. So here the characterization is achieved by the application of surface stains. We have to mark some areas or to put surface stains, like we have to do with markers. We are going to stain any surface. Latest version of Empress ceramic approach, Empress 2, is based upon again lithium disilicate ceramic. These materials can be fabricated to give materials having a flexural strength approaching that of the sintered alumina core ceramics, that is 300 to 400 megapascals. Materials are recommended for the fabrication of 3-unit bridges that are fixed partial dentures. Bridges can also be termed as fixed partial dentures to replace missing anterior or premolar teeth. Now, cast glass and polycrystalline ceramics. Approach to casting ceramic is very similar to that used in pressing and molding. Same as those used in the lost wax technique used in alloy casting. Current systems in this category are used only for the manufacture of single crown and are being replaced by the stronger sintered alumina and pressed glass system. Ceramming, a lengthy procedure. Crowns formed from wax pattern invested in phosphate bonded investment. When we are covering or dipping and filling any wax pattern, or so, and we can say we are embedding a wax pattern. This in any material which is investment material. So this process is called as investing or invested. Wax pattern is invested and investing. And this is in phosphate bonded investment material. As already described, that phosphate bonded investment material is a universal investment material. Wax burnout and heat soak of investment carried out at much higher temperature, at 950 degrees centigrade. Molten ceramic is cast centrifugally into the mold at around 1350 degrees centigrades, and this results in a transparent glass crown, and which is then heat treated in an oven at 175 degrees centigrade for 10 hours. A lengthy procedure. So jao. This heat treatment or ceramming causes partial crystallization to form mica-like crystals. And these mica-like crystals contains potassium, magnesium, and silicon oxide, and significant quantities of fluorides. And all you know that fluoride has dual effect. Slightly reduces the translucency of the previously clear material, but the all these material along with the fluoride significantly increases the strength of these cast ceramics can match that of aluminous porcelain. Color matching is achieved by applying a series of appropriate tinted porcelains to the surface and refiring. Apply tinted porcelain and look at if it appears correct, it's clear. Otherwise, you can do refiring. This procedure may be circumvented with the development of new candidate material in which the shading can be incorporated within the body of the crown. Further improvements, and again more further improvements in appearance achieved by selecting correct shade of luting cement, because this material is transparent. Surface glaze should used to provide color to cast glasses. Now these glasses are cast. No any metal casting. Cast glasses can produce a very realistic result. Problem: if there is a need to undertake any adjustment of the shape of the crown, they are rapidly removed, resulting in poor aesthetic unless crown is reglazed. The technique of casting offers the ability to produce accurately fitting all ceramic crowns, because we are now accurately producing the fitting surface of that ceramic crown over the die directly. No intermediary aluminum foil is there, so fit is accurate. Strong enough for use in the posterior region. It is as strong as a metal porcelain fused to metal. So we can use it in posterior region without the need of an alloy substructure which is present in the porcelain fused to metal material. The need for some special equipment may be considered as disadvantage. Now, yttrium tetragonal zirconia polycrystal, Y-TZP or ZP. This is the another system, yttrium oxide blended with zirconium oxide to generate multi-phase material, and it is also known as partially stabilized zirconia. These restoration may be processed using casting procedure or may be partially or fully sintered materials. Both things can be performed with these materials. Milled mean monolithic blocks, casting procedures, or may be milled from monolithic blocks of partially or fully sintered materials. Monolithic blocks, I will show you. These are blocks. Monolithic mean in one structure. Very high values of flexure strength, 900 to 1200. You have seen in the table. Megapascal and fracture toughness due to polycrystalline structures are there. Process of transformation toughening caused by changes in crystal structure by internal stresses. Transformation results in localized increase in volume, which cause again the compressive stresses to be set up around crack tips. The phenomena already described in the previous lecture, and this reduces the likelihood of further propagation of the crack. Now, the CAD-CAM restorations. CAD-CAM stands for Computer-Aided Design and Computer-Aided Manufacture. We have discussed it in previous chapters. A high-tech approach to providing patients with a durable tooth-colored restoration. It involves recording of an optical impression in computer. There's no need of taking impression of the patient through any impression material. Only have to take the picture, and it is called as optical impression. Design details used to construct a restoration by using a computerized milling machine which cuts the desired shape from a monolithic block of ceramic. Monolithic block, I'll show you inshallah. Now, material and care. Care is required during cavity preparation to ensure that there are no undercuts within the cavity. If there will be undercuts, so CAD-CAM material should be difficult to, it can make, but you people cannot fit the prosthesis into the cavity because of that undercut. This technique is relatively flexible in terms of the shapes of restorations that can be made with modern milling technology. Now, complex 3 or 4 surface restorations are possible, including even the replacement of cusps. In addition, it is possible to manufacture ceramic veneers using the latest generation of these systems. For example, CEREC 3.1. Optical impression. The optical impression is recorded using a miniature video camera. Video camera is there for recording the impression. Scans prepared tooth for about 10 seconds. Only 10 seconds needed for taking the impression. Prepared tooth surface be clean and dry and coated with an optical reflective powder to maximize image acquisition. For accuracy, coated layers should be uniform and thin. Opposing teeth captured to recreate the normal pattern of interdigitation. Interdigitation means when tooth comes into the close contact with each other to create an appropriate surface anatomy for the restorations concerned. Now the design of the restoration on the computer screen takes only 10 to 25 minutes depending upon the complexity of the restoration and the extent to which the software is asked to accommodate the patient's occlusion. Again, the milling process only takes 5 to 10 minutes, varying with size and complexity of the procedure. Adjustments. Restoration is tried in and adjusted if necessary. Try-in is easy for more complex shapes as due to small screw on the finished restoration can be used as a handle with the handle while manipulating it. Normal to etch the ceramic fitting surface with hydrofluoric acid as already described. Then apply a silane coupling agent to aid retention before final cementation and use dual cured resin cement. Polishing. Final polishing can be performed in situ. Situ means when you have placed or fixed the restoration into the patient's mouth. Not possible to provide a glaze in CEREC system. The beauty of CEREC system is that all stages of preparation and manufacture can be undertaken in the dental surgery. If you have 2 or 3 crore rupees, you can buy this system. However, it is a relatively time consuming process as a consequence because if we take all the procedure, we have to give 3 to 4 hours to our patient. Cutting will take about 1 hour and 1 hour for the manufacturing and 1 hour for the setting into the patient's mouth. It's in quite lavishly allocated time. Alternate of CAD-CAM are also available. Mechanical copy milling technique in the laboratory. Clinical stages are identical to those for a conventional inlay. Pattern is produced in the laboratory and replica of the pattern produced in ceramic using a copy milling device. Commercially available systems are capable of reproducing both relatively intricate fitting surfaces and occlusal surfaces of the inlay. Material used for the ceramic block from which restoration is cut include conventional feldspathic porcelain and glass ceramic. Recently, restorations can be cut from sintered alumina blocks, which can be infiltrated with glass to form in ceram like CAD-CAM restorations. A variety of approaches to providing CAD-CAM restorations are now available to dentists. To avoid the expenses of buying equipments, there are specially licensed laboratories also there. Advantages of CAD-CAM. Ceramic manufacturing processes include forming and heat treating are under the control of the manufacturer and are taken away from the dental laboratory or clinic. and maximizing the physical properties of ceramic itself. Luting cementation in of CAD-CAM restoration normally involved dual coat composite lutes already described. Lute is potentially the weak link in the restoration as it is much softer than either the ceramic restoration or the tooth enamel that is having 20 Wicker hardness number compared with more than 300 Wicker hardness number. Lute margins of CAD-CAM restoration typically 60 to 150 micron wide, but are sometimes reported to be even wider. The lute can undergo rapid wear to a depth of about half the value of the width. A 50 micron defect surrounding the restoration is normal. Improvements in marginal fit, which will come as impression and milling techniques develop, will help to overcome this problem. Porcelain veneers. Porcelain veneers offer a means of improving the appearance of stained or discolored tooth or teeth. Already described the porcelain. They consist of thin shell-like structures fabricated to closely adapted to the prepared tooth. Controversy that veneers can be attached to unprepared teeth, a technique which conserves sound tooth substance or some reduction in tooth contour is necessary. Most authorities do advise the removal of about 0.5 millimeter of labial enamel as the porcelain veneers are present on labial or buccal surfaces. Now the bonding veneers are normally 0.5 to 0.8 millimeter thick, constructed from feldspathic porcelain or feldspathic porcelain, glass ceramic, pressed ceramic or CAD-CAM techniques, bonded to the tooth enamel using a composite resin loading agent. The bonding achieved by etching the enamel with phosphoric acid solution or gel. The fitting surface of the veneer is etched with a solution of hydrofluoric acid. It is already described many times. Dried and treated with a silane coupling agent to aid bonding to the composite resin. The appearance of the veneer tooth depends on the color of the underlying tooth structure, aesthetic qualities of the ceramic, correct shade of luting composite. And these are required to mask any discoloration in the underlying tooth and give a natural appearance. Use of a light activated luting composite due to extended working time during which the veneer can be placed accurately is necessary. Shade. Accurate assessment of the shade of a porcelain veneer cannot be made at trial without coupling the veneer to the underlying tooth. This process involves optically linking the veneer to the underlying tooth to see what effect the color of the tooth has on the finished restoration. Simply, what you have to do, you have to wet it using water and place it over the tooth. And if you have enough money, a better alternative is the water-soluble trial paste. This commercial product has similar color characteristics to the luting resin but can be washed off the veneer surface with water prior to luting the veneer in place. And the clinical achievement, in some respects, the apparent clinical success which has been achieved with porcelain veneer is surprising. Technique involves the support of a very thin, rigid and brittle material, the veneer, by a more flexible material, the luting composite. It would be expected that cracking of the ceramic would be a frequent occurrence under such circumstances. Due to the mismatch, the fact that this does not appear to be a major problem suggests that stresses generated are not greater enough to cause a strain of 0.1%, critical strain above which most ceramic material will fracture. Alternative to the porcelain veneers involve the use of preformed acrylic veneers or polishable composite resin veneers. Acrylic resin veneers we have discussed, and inshallah we will do in practicals. Ceramic materials are more durable due to greater hardness. Fabrication is more time consuming than the direct method of using a veneering composite. The performed acrylic veneers seem to offer few advantages. Preformed acrylic veneer. They combine an involved clinical and laboratory technique with poor durability, because acrylic is having much less strength. Porcelain fused to metal. Porcelain fused to metal, PFM. Restoration involves a marrying of the good mechanical properties of cast dental alloys with the excellent aesthetic properties of porcelain. शादी हो गई है इनकी. Generally, the restorations consists of an alloy substructure with bonded porcelain veneers. A major requirement of the material used in porcelain fused to metal restoration is compatibility of the metal and ceramics used. Feldspathic porcelain used for porcelain fused to metal works normally contains significant amount of lucite, already described. Mica-like structure or other one. What is lucite? Now, this is up to you, that what is lucite structure and how it produced. Lucite increases the coefficient of thermal expansion of the porcelain to a value which is closer to that of the metal, and also prevent the development of thermal stresses during cooling from the firing temperature. The presence of lucite also helps to strengthen the ceramic. Maximum flexural strength required for porcelain fused to metal ceramics in ISO standard is 50 megapascals. Now, equivalent to the requirement for dentine enamel porcelains used in all ceramic restoration. Which thing is equivalent? It is 50 megapascal. Now, requirements of alloys for substructure of porcelain fused to metal, similar to those for non-porcelain bonding work, and we have discussed in the previous chapter. Which one? In the metals. Now they have some additional requirements, and these are four. Casted alloy capable of withstanding porcelain firing without melting or suffering creep and have a high fusion temperature. Alloy should be rigid to support a very brittle porcelain. Veneer and prevent fracture of it. Alloy capable to form a bond with the porcelain veneer and prevents its detachment. Coefficient of thermal expansion similar to the porcelain to which it is bonded. Types of alloy already we have described in the chapters of alloys. There are four types of alloy currently available for porcelain bonding alloys. High gold alloys, low gold content alloys, silver palladium alloys, and nickel chromium alloys. Properties of alloys used for porcelain. High gold alloys have maximum castability. Creep resistance during firing is not much. Modulus is acceptable. Bond strength is acceptable, and biocompatibility is higher than all of those. Low gold castability again acceptable. Creep resistance during firing is much more than pure gold or high gold. Modulus more than high gold alloys. Bond strength is acceptable. Biocompatibility is acceptable. Silver palladium alloy castability negative, not much acceptable, but nowadays casting techniques are improved, so it is acceptable. Creep resistance during firing is acceptable. Modulus of elasticity equal to the low gold alloys. Bond strength acceptable. Biocompatibility acceptable. Nickel chromium alloys castability much less than high gold content alloys. Creep resistance during firing acceptable, very much acceptable, or excellent you can say. Modulus excellent. Bond strength, that is why our usually chipping off is seen there in bridges and crowns. Biocompatibility highly negative. Now, high gold alloy, major differences between these alloys and non-porcelain bonding alloys are high platinum palladium content, which raises melting temperature, reduces creep during firing, decrease CET to porcelain. Absence of copper as it gives green hue to porcelain. Presence of small amounts of base metal such as tin, because it relies usually for bonding with tin oxide, not with the copper oxide. And indium promote bonding between alloy and overlying veneer. Base metal become oxidized at the surface and the oxide layer forms a chemical bond with porcelain. But again, the bond strength, if you see, is not as compared to much as compared to the other ones. Typical high gold content porcelain bonding alloy is gold 85%, platinum 10%, palladium 3%, silver 1%, tin 0.5%, and indium 0.5%. Disadvantages: melting range is still low, a risk of alloy sag during porcelain firing. Modulus of elasticity of higher gold alloy is less than ideal. Copings must be produced in fairly thick section in order to prevent flexing, which would result in porcelain fracture. Requirement of a minimum coping thickness of around 0.5 millimeter results in the risk of an over-contoured restoration and gingival irritation. And what is this sag? Sag means deformation under its own weight. Now, low gold porcelain bonding alloys contain approximately 50% gold and 30% palladium. To raise the melting temperature and lower the coefficient of thermal expansion, silver and indium 10% and tin for porcelain bonding. Again, tin is the and indium are the bonding agents. You can say mechanical properties similar to high gold, slightly greater modulus of elasticity, which is an advantage for porcelain bonding. Higher melting range produces better creep resistance for these materials during porcelain firing. Good properties and cost saving compared with high gold alloys account for the widespread use of these materials for bonded porcelain work. Now, silver palladium alloy contains 60% palladium, 30% silver, and 10% indium or tin to aid porcelain bonding. Again, higher modulus value and a higher melting range than the high gold alloys due to the higher content of palladium. Suitable alternative to the high gold materials for bonded porcelain work at a considerable saving in cost. At that time, I think palladium is somewhat of low cost. Now, providing care is taken during casting to avoid defects and gas inclusions. A green hue due to the silver taking up of a green hue in some ceramics. Ceramic may take green color from the silver. In contact with high silver content alloy, silver graining is reported. So the green hue is silver graining. Although this appears to be as much a feature of the composition of ceramic as the composition of the alloy. Now the nickel-chromium alloys. Nickel-chromium alloys, casting alloys, are typically containing 70 to 80% nickel and 10 to 25% chromium. Small quantities of other metals like molybdenum, tungsten, and beryllium are also there. Porcelain bonding is to the layer of ceramic oxide which forms on the surface of the alloy. These alloy have the advantage of a very high modulus and high melting temperature. Disadvantage is the high casting shrinkage, which may affect accuracy of it if not fully compensated by the investment. A tendency for poor castability with voids in the castings. Poor castability is there. A bond strength with porcelain which does not compare with that achieved with the other alloys. Fractures. Fractures in nickel-chromium porcelain system occurs through the oxide layer. Fracture in other systems generally occur cohesively in the porcelain. In addition, these alloys are suspect from the biocompatibility point of view. Why? This is assignment. I'm going to extend this assignment. Now, tooth preparation for porcelain fused to metal restoration. It is necessary to alloy about 1.5 millimeter in thickness for a metal coping. That should be 0.3 to 0.5 millimeter, and for the porcelain veneer 1 mm to achieve optimal aesthetics. This space, if not available, then the technician will either produce an overlay bulky restoration with reasonable appearance, or the opaque layer of porcelain used to mask the metal coping. And this opaque layer will shine through the surface layer of porcelain, this metal surface, which otherwise will shine through the surface layer of porcelain, producing an opaque white or cream spot. Now this opaque layer will produce an opaque white or cream spot on the surface. For this reason, preparation for porcelain fused to metal crowns need to be designed to give adequate space for the technician to produce an appropriate restoration. Shoulder and chamfer already described in the previous lectures. Margin configuration for a porcelain fused metal crown should be flat shoulder where there is porcelain and a chamfer or bevel where this is a metal finishing line. The appearance of the margins of porcelain fused to metal crown has been revolutionized by the development of shoulder porcelains. These porcelains have adequate substantivity so that they do not flow significantly during firing. This allows the technician to cut the metal coping back from the edge of the tooth, leaving an adequate bulk of porcelain to give a reasonable margin fit with much improved aesthetics. Chamfer preparation, you can see this is the chamfer, and shoulder, this is the shoulder 90-degree chamfer, you can say bevel shape. Now capillary technology, capillary technology system is an alternative mean of producing porcelain metal restoration. Metal substructure is produced in two stages. First, a wax strip bearing powdered high palladium content metal adapted to the cast, fired in order to burn off the wax and sintered the metal, forming a three-dimensional capillary network. Second stage, another wax strip loaded with almost pure gold, 97% pure, applied to the surface of the sintered layer, fired wax again burnt off, and the molten gold infiltrates the capillary network to form a metal substructure with the composite structure. A thin layer of veneer porcelain is finally baked onto the surface. This layer is only about 35 micrometer thick, as it does not cover any dark oxide because no oxide layer is there. Bonding between the metal and porcelain is achieved through mechanical attachment. Now, bonded platinum foil. A problem with the metal bonded porcelain restoration. A considerable thickness of tooth substance must be removed to allow space for the metal coping and the porcelain veneer. An alternative approach, adequate in some circumstances, is to make a porcelain crown which is bonded to a platinum foil. Technique involved layering down two platinum foils as already described in the previous lecture on the working die opposite to the normal single foil surface of the outer foil, then tin plated and porcelain constructed and fired on top of the tin plated surface. Porcelain bonded to the layer of tin oxide on the tin plated surface. Inner foil removed prior to cementation of the crown. One platinum foil remains bonded to the inner surface of the crown. This foil helps to prevent crack formation on the inner surface. Now, one thing, the monolithic block. I want to show you where is your monolithic block. So you people have an idea. So I am going to show you the monolithic block because some pictures are not there. So in your monolithic block, it is there in your book, but as all of you are afraid of your books and not going to see your own book and seeing and consulting other books, so it's my duty to show you your books at least in my lectures that this is the book which you people have to study. So I'm doing my duty and you are doing your duty of not seeing the books. So I think this. So now you can see this is your monolithic blocks for CAD-CAM restorations. These can be milled like this, and you can hold through this part and can check by placing it over the tooth of your patient. So this is the milling machine. This is your monolithic blocks, and this is the CAD-CAM machine. Here the camera and other things I will take it there. This is the designing machine, and sorry, this is the designing and impression taking machine, and it is the milling machine. So I think nothing will be there. No, 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 no. It is the end of your. I think nothing is there to show you people. And also you can see that how each and everything I have highlighted for you people, and for making your lectures. So it's not an easy task. My ambitions are to give you as much as knowledge as I can. So waiting for your precious comments. Allah Hafiz.